That sounds mighty awesome.
Butler, this is a 20-minute AMS math talk. You're done.
Okay.
I know.
Steve Butler, preview for this weekend talk.
Okay, so I will warn you, I just barely finished the slide, so I don't know how long this will take. It'll either be a 10-minute talk or a 45-minute talk. But hopefully it's about right. So order multiplicity inverse eigenvalue problem for graphs on 6 vertices. There's actually a footnote here. Well, almost all graphs. There's one small case we didn't quite do, but well, we'll fix that. That should be done soon. So this was done at an REU, and so these are all the people who worked on the project. Christine and Josh and Michael and me. That I'm easy to find out. I'm usually the tallest one. Then there's Audrey and Beth and Haley and John and Cassandra. Now, you might say to yourself, "Boy, that looks really fun to be in an REU. You get a cool T-shirt. You get to spend the whole summer. Can I participate? After all, these people were able to be in the REU." The answer is yes, you can. We're going to have another REU in 2 years. Michael's going to be doing something. I'm going to be doing something. Other professors are doing something. Start campaigning now to be part of those REU projects. Okay, so anyways, we're going to talk about what we did. Very good group, by the way. Hopefully we can get 1 or 2 of these people to come here for graduate school. So we did something in combinatorial matrix theory. So we're going to talk about matrices and graphs. And what happens here? Well, the idea in spectrograph theory is you have a graph, you associate it with a matrix. The matrix has eigenvalues. What do the eigenvalues tell you? But of course, the question is, which matrix? And so in spectrograph theory, you have all these people who study adjacency, and then another group that studies Laplacian, and another group that studies the best matrix of all, the normalized Laplacian, and so forth and so on. So instead of just picking one matrix at a time, let's just say, let's look at all the matrices simultaneously. So we're going to create this large collection of matrices. So this is the collection of all real symmetric matrices whose off-diagonal nonzero entries are prescribed by where the edges are. The diagonals are arbitrary. So basically, almost every matrix you've ever heard of in spectrograph theory is included inside of this set. So this set is huge, it's massive, to the point where you can ask, what can we possibly know about this set? Well, here's a fairly simple problem. It's called the inverse eigenvalue problem. And it says, well, suppose you know your graph, G. What are the possible spectrums? In other words, the possible set of eigenvalues that you can achieve for matrices in this set. Well, it sounds like it should be an easy problem. And how hard could it be? But I remember a conversation I had many, many years ago with my then advisor, Wayne Baer, and he said, well, if you pick a random graph on 5 vertices, we don't know the answer. Now that was years ago. We have improved since then, in that now we know it for 5 vertices. And so this is the state of the art. We know the problem completely for graphs on less than or equal to 5 vertices. 6, not done, and hence why we did our REU. Now, this was a group project. A couple of these people actually were from Iowa State. Michael's on that paper. Leslie's on that paper. Dr. Lin, who's now at the University of Victoria, is on that paper. What were big ideas? What was the big tool that let us make progress on it? Well, the most powerful tool was something called the strong spectral property. And if you're familiar with the strong Arnold property, it's a generalization of that property. And it says the following. Suppose I have a matrix A. So A is fixed. And we say that the matrix A has this property if the only symmetric matrix X, where if I take the entry-wise product, gives me 0. When I take the identity times the entry-wise product with X, gives me 0. So this essentially tells me where the 0 non-zero entries are. AX minus XA is also 0. So the only solution there is X equals 0. All right. Well, why would we care about this property? And in particular for the inverse eigenvalue problem. And the reason is the following theorem. Different Baird et al. Paper. This one has actually already appeared. And it says the following. If you have a matrix which has this property, this really cool property, and it's associated with the graph. If you take a supergraph, so add edges, so you run add vertices, just edges, then there's another matrix that's associated with this new graph, has the same spectrum. So in other words, once you have something for a small graph, you get something for a lot of bigger graphs as well. So it allows you to sort of kill many birds with one stone. So this was able to dramatically reduce the amount of work that has to be done. So that's what's known. What did we do? What's our problem? Well, we're not going to do the inverse eigenvalue problem. We did make a lot of progress on that. Instead, we focused on a simpler case called the ordered multiplicity problem. We said, well, what ordered multiplicity lists are attainable for connected graphs on 6 vertices? Well, what are ordered multiplicity lists? Well, for that, you say, okay, look at your spectrum. And because we're dealing with real symmetric matrices, the eigenvalues are real, and so we can order them. And we can look at how often does each eigenvalue occur. So that gives us an ordered multiplicity list, gamma 1, gamma 2, up to gamma k. Oftentimes, we'll just delete the parentheses and just write down the multiplicities. So that's an ordered multiplicity list. And now, what are we going to do? Well, we're going to tackle this. Now, there's 112 connected graphs. There's 19 possible ordered multiplicity lists once you take care of symmetry, because if I have a matrix, I can negate it, which essentially just says I can reverse. So I can narrow things down. That gives 2,128 cases of possible things where you have a graph and an ordered multiplicity list. We know this for 2,127. So there's just one outstanding, and I'll point it out in just a second. And I will say that for most cases where we have attainability, the spectrum is arbitrary. We're down to 40 cases, give or take, where we don't know. So we're very close to actually doing the whole inverse eigenvalue problem. So we can summarize our result in this very easy to understand diagram. So here it is. So these are all connected graphs on 6 vertices where we're using the atlas of graph numbering. And this is the complete graph up here. This is the path graph down here. And this is just the empty null there for convenience. And blue vertices correspond to graphs which are unique. In other words, those graphs are the only graphs which achieve a certain family of spectrums. No other graph can achieve the same set of spectrums. Yellow
So those
vertices.
graphs could be described as determined by their ordered multiplicity lists.
Those graphs are determined by the possible order multiplicity list. Absolutely. And there's a non-trivial number of them that do that. The ones in yellow are ones which are part of big families. And so to help us to make the readable, we put the big families off to the side. And you can, if you're really patient, actually use this to determine what is possible for any order multiplicity list. Find your graph, and then as you follow the path down to the empty set, these are actually labeled with ordered multiplicity list. So 1, 2, 3, 2, 2, 2, so forth and so on. And so anything that you can achieve by path, that's what is possible for ordered multiplicity list. So this is actually a really condensed way of doing this. If you look at the paper, there are 16 pages of appendices, which is basically this diagram unraveled. And it's probably more useful if you look in the appendices, but it's nice that we can condense it to a single picture. All right, so here we go. Since we're at Iowa State, talking in a discrete seminar, there's a rule somewhere that says we have to use zero forcing. So we're going to talk about zero forcing, semi-definite zero forcing, and Q. We're not going to define these because you're going to hear that in other seminar talks in the future. But suffice it to say, you must learn this at some point. So the important thing for us is what is zero forcing. It's a nice combinatorial property that helps us bound the maximum nullity of a matrix in our set S of G. Z plus is very similar, but it bounds not maximum nullity, but it bounds maximum nullity for semi-definite matrices. So in other words, it's just for a small slice of S of G. And then this last one, Q, is not a combinatorial parameter, at least not yet. There are some combinatorial bounds, but it's a minimum number of distinct eigenvalues. And there's a nice paper by Bjorkman et al. This is our Beth Bjorkman, who insists that there are no umlauts in her name, but that's okay. So she is the world's expert on Q, and so, well, of course, also Carolyn right now. I'm sorry, Carolyn, you are also the world's expert on Q. Well, we have the world's expert on Q in this room. So I'm sure we will hear at this some point in the future. We'll get to hear a nice talk about this. So here are 3 parameters. Well, what can we do with this? Well, the zero forcing number.
Going on the line, you should point out that Q was introduced by Sean Fallis Group in the China.
Q was introduced by Sean Fallis Group. All right. So what can we do? Well, you have the zero forcing number. What can that do? Well, that can rule out multiplicity lists that have any term greater than z, because essentially the zero forcing number bounds your maximum multiplicity of an eigenvalue. The semi-definite zero forcing number rules out the maximum multiplicity on the ends. In other words, the first entry or the last entry of the multiplicity list. And the minimum number, Q, it rules out multiplicity lists which are too short. It turns out that these three parameters basically get about 95% of the work of saying what's not attainable. So some very simple things can rule out most things which aren't attainable, not everything. There are a few other things that we need. Here are two of them. If you have a graph which is connected, odd unicyclic, well, that means that one cycle, and it has a cycle that's an odd length cycle, then at least one of the first or last multiplicities has to be 1. This follows from prone Frobenius. So for instance, I can't have a 2, 2, 2 if I'm odd unicyclic, because both the first and the last are not 1. And there is a similar result, a little bit more technical. If you have a generalized star, or generalized threeson, and a generalized threeson is you take a triangle and you put paths on the end. So this is a generalized threeson. And it can obtain a multiplicity list with consecutive multiple eigenvalues. So 1, 1, 2, 2, 1, 2, 2, 1, so forth and so on. So that's ruled out for this as well. Okay, so those are some of the tools, and we'll give a few more things which aren't possible. But let's talk about what is possible, establishing attainability. So there's a few things we're going to use. There's the strong spectral property, where we can build off of what was already known for the inverse eigenvalue problem result, because a lot of the smaller graphs on 5 or fewer vertices tend to be able to achieve things being spectrally arbitrary, and with SSP, that lets us build off of things really nicely. You get orthogonal representations, and occasionally we get SSP for some of those. There's cloning, which we'll talk about more. There's graph minors, and there's miscellaneous constructions. So when in doubt, at the end, we just sort of pounded away. Some of those undergraduate students were amazing at this. Audrey in particular was fantastic, fantastic. I don't know how she did some of those constructions. What's graph minors? I'm not going to talk about it more than this slide. It says if you have a minor of a graph, so G prime, it's a minor of G by contraction, one contraction, so there's one fewer vertices, then if I have something in G prime with an ordered multiplicity list, then I can just take that ordered multiplicity list and get an ordered multiplicity list for G, but I put a 1 on the end. So I either add a largest eigenvalue or a smallest eigenvalue. Now that 1 for ordered multiplicity doesn't seem very important, but it might really be a really big one. So the theory says, look, there's the big eigenvalue way out at the end, and it might be really big, but ordered multiplicity, we don't care. Okay, so let's talk about orthogonal representations. So let's start with a very simple case. So here's a graph, 6 vertices, and we're going to associate each vertex with a vector, in this case a 4-dimensional vector. And so I'm going to just put my vectors representing my orthogonal representation in a row. So this is V1, V2, V3, so forth and so on. And I'm doing it in a particular way. Now, what do I mean by orthogonal representation? Well, if two things are not adjacent, so for example V2 and V3 are not adjacent, then the corresponding columns should have be orthogonal. So you can check 2 plus 0, minus 1, minus 1 is 0. On the other hand, if they are adjacent, then the corresponding columns should be non-orthogonal. So in other words, their dot product should be non-zero. Now A is not yet specified, which is to our advantage in a moment. So this is what an example of an orthogonal representation is, and it's a very useful thing to do. Well, what do we do when we have one of these? Well, we take M transpose times N. Now the nice thing about this is that this matrix here, first off, if I look at the 0 non-zero pattern, it corresponds to the graph. That follows from orthogonality. If I look at the eigenvalues are actually fairly easy to compute. There are going to be 2 zero eigenvalues because of just the dimension of this. And because we went the extra step, and you didn't see this right away, but these rows are also orthogonal. So it's the norm of the rows are going to give us those remaining eigenvalues, which means that it's actually a very easy spectrum to compute. So the eigenvalues are 0, 0, 4, 4, 4 plus a squared, 4 plus a squared. Now, it doesn't automatically follow. It has SSP, but there's ways to check, and it does. And so this is just sort of a bonus. If we fiddle with these parameters A here, and then we scale and we shift, which are perfectly allowable things to do, we can see that this attains ordered multiplicity list 2, 2, 2, spectrally arbitrary. And as a bonus, because it has SSP, then we get all the graphs which contain as a subgraph. So there's a lot of graphs on 6 vertices which contain this as a subgraph. all of those also attain 2, 2, 2 spectrally arbitrary. So that's an example of a way we would knock out 60 cases at once. So that's how we were able to make a lot of progress in a little bit of time. Okay, so let's talk about clones. So we have two ways to clone. You might call this duplication. We can,
Also 20.
or 20. There's a lot of good names. We found clone was the most useful because we're going to do the opposite. We're going to do what's called decloning, which is hard to say with deduplication or detwinning, but so what does it mean? Well, essentially I pick a vertex and I duplicate it, or I clone it, I make another copy. Now I can do it in two ways. I can either make it so the new copy is not adjacent to the original one, or I can do it where the new copy is adjacent to the original one. So more or less, it's sort of what you think it should be. I'm making a vertex which has the same properties. It may or may not be connected. Okay. Well, how do we use this? Here's the theorem. If I have a matrix for my graph, and it has a nice ordered multiplicity list, M1 up through MK, and I now clone. So I just take one vertex and I clone it with an edge. With an edge is important here. Then I can get a new graph in this clone version, sorry, a new matrix from this clone version, where it's the same multiplicity list except the first entry goes up by 1. Okay, so that allows us to make a little bit of progress. As a bonus, we have the same set of distinct eigenvalues. So more or less we can maintain spectrally arbitrary. So if I start with something spectrally arbitrary, clone, the result is spectrally arbitrary.
Couple of questions. Is that
Sure.
an ordered multiplicity list or just a multiplicity list?
It's an ordered multiplicity list because it's a list. Lists are naturally ordered.
But are you ordering them by the ordered multiplicity list means in the order of the eigenvalues?
Yes, that's how that was defined.
Okay, so you're always putting it on the bottom one.
Yes.
Okay.
Or by symmetry, I can put it on the top one. Now, the reason that I insist it's on the bottom is that there's this extra advantage that happens. If I put it on the bottom, I'm dealing with a positive semi-definite matrix, and that because I'm dealing with something which is connected, this is an assumption I didn't throw in here because of space, but I'm assuming I'm dealing with connected graphs because of the problem. I know that I'm cloning with an edge always because it's a non-zero diagonal.
Because otherwise you'd have an issue with what the diagonal is.
Right. So you can actually clone and increase things in the middle, but the problem is you have to be a little bit more knowledgeable about what the diagonal element corresponds to, whether it's 0 or non-zero. And so we'll go through and do that a little bit later. The kite we know achieves 2, 1, 1, 1 and 1, 1, 1, 2. That follows from the Barrett et al. Paper. And so we can say, look, here's this kite. This is the kite. Clone the little tail of the kite with an edge, and you get this graph. And so this clone graph, I can increase the first entry. So 3, 1, 1, 1. I could increase the first entry here, 2, 1, 1, 2. And of course there's symmetry, so 1, 1, 1, 3. So that's another way that we were able to make good progress. Cloning worked really well because SSP does not work for everything. And the higher up you go, it starts to not be quite as potent as it was for small graphs. Okay, now let's go back and do unattainable cases. And we want to show there are some things which we can rule out. And we're going to do it by decloning, which is the opposite of cloning. So I guess I should say, how did cloning actually work? And we've got to peek a little bit under the hood. The idea of cloning was we think about an orthogonal representation, and we're saying, look, it's the same vector, we're just going to copy that vector again. That's the idea, we're cloning that vector. So decloning says, I have two vectors which are the same, I can pull one out, and then I don't really lose anything. So that's the idea of decloning. So there's a little bit of work that goes into it. So looking at time, I'm going to skip this argument, and I'm going to focus on G125, because this is sort of a nice, interesting case. So why can't we achieve ordered multiplicity list 1, 3, 2? Well, most of the arguments are very similar to what we're about to see here. So, proof by contradiction. Assume we can. Well, if we could, then there has to be some matrix with the spectrum minus lambda, 0 with multiplicities 3, 2 with multiplicity 2. I can do this by scaling and shifting. So that's perfectly allowable. So if there is a 1, 3, 2, there is a 1, 3, 2 with this spectrum. Okay, now I'm going to label my graph and I'm going to focus on this vertex. If that diagonal entry was not 0, when I clone, I get this graph. And because I'm cloning, I'm actually going to increase the nullity here. So go up and have nullity 4. Now that doesn't seem so bad, except for all of you zero forcing aficionados, these three vertices are a zero forcing set. So we can force down, and then you can force down, and you can force, and then you can force. So it would have nullity 4, but a zero forcing set of size 3, which is impossible. And so therefore, it has to be the case that M55 is 0. But if M55 is 0, M66 is 0 by symmetry. So this is good. Now, it turns out, and details are not important, but because these are both 0, it actually says these two have to be scalar multiples of each other in a nice orthogonal vector representation. Ah, great. Well, now that we know that the vectors that correspond to these vertices are the same up to scalar multiple, I can declone. Okay, so I'm going to declone. Essentially, think of it as deleting one vertex. But I'm still going to attain a lot of the same properties. What will be the effect? I'll be on 5 vertices, and I'm going to lose one eigenvalue of 0. Okay, so here we go. We now are to a graph on 5 vertices. Here's the corresponding matrix. Because we started with a 0 entry, we still have a 0 entry. What else can we say? Well, we can say have rank 3. It's because we still have the same non-zero eigenvalues. All right, well, that's not so hard. The first 3 rows are linearly independent. Well, that's not hard to see, because if I look at where these pivots are, that's clearly they're linearly independent. Which means that the bottom 2 are linear combinations of the first 3 rows, which means, in particular, that C4 and C5 have to be a multiple of C2 and C3, respectively. So if I scale these, I get those for some non-zero number. Okay, so far so good. Well, now here's the tricky part. If I look at n minus I squared, and this is why we chose our eigenvalues to be 0 and 2, it turns out that this spectrum has a multiplicity of 4 for the eigenvalue 1 and one other eigenvalue. This forces that this matrix R corresponds to a main graph which is a clique and some isolated vertices. Well, what's important about that? You can check that the dot product of the first and the third rows is non-zero, because C1 times C2 is not 0. So that means that 1 and 3 have to be in the clique. On the other hand, the dot product of the first and the fifth row is 0, which means that 5 is not in the clique, which means it's isolated. Which means that if I look at R2, 5, well, there can't be a connection between 2 and 5. So that has to be 0. But we can do the computation. If I take the dot product of 2 and 5, that's C2, C4 plus C3, C5. Now I can apply what I did up here. So that's alpha times C2 squared plus 3C squared, C3 squared, sorry, which is not 0. And that should say, oh, that's bad. Because 0 is not 0 is a bad thing in mathematics. So that's a contradiction. Which means something was wrong. Well, the only thing that we assumed was that we could attain this 1, 3, 2. So that's how we can show that we cannot attain 1, 3, 2. Let me just briefly mention K33 and 1, 4, 1. It's easy to show that the adjacency matrix for K33 has a spectrum -3, 0 with multiplicity 4, and positive 3. And the gaps here are both 3. So it's nicely spaced on both sides of 0. And you might say, okay, maybe can we do anything else? And the theorem is no, that's it. Whatever matrix you achieve for 1, 4, 1, that's the order of multiplicity, for the graph K33, you have to have nice spacing. So in other words, the space between your smallest and your middle, and the space between the middle and the largest has to be equal. I'll skip that, but I will say that we believe this is the only graph on 6 or fewer vertices where, when we can attain an order multiplicity list, we cannot do so spectrally arbitrary. All the others seem to say that you can do it. Even the ones that we don't know, we can do it for a lot of different spectrums. And so we think this is sort of the unique first special case. Okay, some remarks. This was done at Iowa State for the REU, was supported by the NSF. There's the grant number. A lot of stuff still to be done. Of course, there's the inverse eigenvalue problem for graphs on 6 vertices. And you can tackle the order of multiplicity for 7 vertices. Of course, you can imagine that, just every year you increase by 1. If you did 6, do 7, and so forth and so on. Of course, if you're going to do that, that's going to be hard. It might be easier to focus on special families. One family that seemed to be really interesting were clique stars. That's cliques joined out of a single vertex. They will show up surprisingly often as unusual cases. And of course, look for more tools. SSP was a great tool, but it's running out of steam. We're going to need new tools to keep pushing forward. And my time is up, so thank you. I think I only have like 2 minutes for questions.
Okay. Any questions?
One of the tools you used was at the beginning you had a sparse graph on 6 vertices. It was the cycle with 2 leaves on, and you could conclude a lot of things about that because you knew that one.
Right.
Could you do that generally for n vertex graphs if you have some nice sparse graph that you know a lot about? And since you can conclude things about the supergraphs of it, then you could say X number of, or a percentage of the graphs are known.
Yeah, in fact, so a lot of the stuff we did for 6 vertices can be automated. So using the tools for SSP, using cloning, all sorts of things. So we took what we did for 6, we threw it on to 7, and we've got like 94% done for 7 in terms of order of multiplicity. So yeah, you can do a lot, but it's that other 6% which seems to be interesting, and just it's hard to make progress on.
I'm just curious if you could actually say that we know the answer for 50% of n vertex graphs for arbitrary n.
I don't think I'm that optimistic, but you get a fair amount, especially if you don't have very high multiplicities. If your multiplicities are fairly small, then you can get a lot of results. So for example, it's known if you want distinct eigenvalues that you can achieve it for any graph and be spectrally arbitrary. So that's known.
More questions? No? Let's thank Steve again.
As we transition to our next